Okay, so this afternoon's class will begin at this, and we may take 2 breaks, and in total it will take about 2.5 hours in the afternoon's class. So let's welcome Professor Mulligan to continue his course with us.
Okay, so thank you very much. Okay, so we will change up a little bit. I'm going to do a little bit on how to evaluate levels of contamination and so on, some of the methods. And then I will go back to some of the methods of decontamination. So we kind of switch it up a little bit. So, sorry. Okay, so in the US, in particular, a lot of the decontamination levels that you are trying to evaluate whether a contamination is a problem or not, you have to look at what kind of risk is involved in that contamination. So there are two things to look at in particular. For the risk, you have to look at what is the probability that you will be exposed to that contamination, and then what is the severity of that contamination. So those are the two things that make up a risk evaluation. So severity can be measured in different ways. So say, for example, it could be measured in terms of how many days you lose of work, how many days you're in the hospital, how many days you have a sickness that you cannot do very much of things. So things like this. So these are how you can look at the severity. Thank you. And then you can look at what is the probability of that risk. So there's always a risk of exposure of something, because you have like what you call the background risk. So it's sort of the normal risk that everybody's exposed to. And then if there's something that's more severe, then you have an incremented or an increased level of risk. So how to evaluate this risk? You have to know, obviously, what chemicals are going to be at that particular place. And then, of course, what kind of exposure there might be. So there are different things that you can do. You can look at how the contaminants are going to be moving. So like some of the transport elements that I mentioned earlier. So things like the movement due to groundwater, movement due to diffusion, all of these type of things will allow the contaminants to move. And then, of course, there's the type of chemical you have. So then you would have to know what kind of toxicity there is of that particular chemical. And so these are the part of this risk assessment. So yeah, so you need to know what kind of chemicals there are. So both in terms of how much there are, what concentration, and how it's distributed. Like where is it found? Is it in the soil? Is it in the groundwater? Is it in the air? And how are they going to move? So sometimes it's difficult to do, because maybe if you have a mixture of chemicals, maybe some will move quickly, some will move slowly, and so it becomes very complicated sometimes. Yeah, so all of these things that you need to be able to do to evaluate the hazard of this thing. So basically, you need to do the site assessment for the chemicals and so on to see where they are, what was potentially at that site. So a site history is very useful. So to know what that land was used for in particular. So what was there? Was it an industry? Was it residential use? Was it municipal use for management of contaminants? What was at that particular place? Because once you have an idea what is there, what kind of activities, then you can get an idea of what kind of things might be happening at that site. You need to obviously then go about trying to determine what levels of contaminants are in the air, the groundwater, the surface water, soil, sediments, things like this, all to get a complete picture of everything. And then, of course, you need to know how the contaminants are going to be moving. You know, so say, for example, if it's in the groundwater, is there going to be a potential to affect a groundwater well further downstream, things like this. So you need to know the geology, you know, of the site, the hydrogeology of the site, where there's the groundwater characteristics, and obviously the climate and the atmospheric conditions as well. So to be able to look at the exposures, you need to know where the chemicals are going to be going. So what is the source? So, you know, where is the chemical initiated? Is it a lagoon? Is it contaminated soil? Is it in the groundwater? Things like this. And then how is it going to be transported? So is it going to move from the soil to the groundwater? Has it already moved from the soil to the groundwater? Or is there the potential for absorption that might slow down the movement of the contamination? Is there the potential for biodegradation? How will the people be exposed to this contaminant? Will there be like a groundwater well that they may be drinking from? And things like this. So these are the type of things to look at the exposure rates. So this just gives you some idea. You have some dump, say for example, of the various contaminants. You might have some of the contaminants might be volatilized into the air. People might be exposed through the wind. There could be some chemicals that could be leaching through the ground and then can go into the groundwater as such. And then people could be ingesting it via the drinking water, through a drinking water well, something like this. So these are some examples of exposure pathways for various contaminants. So yeah, so from the atmosphere, very complicated. I'm not going to go through all of this. Maybe I'll go through the one for the soil a little bit. Oops, no, I don't have it here. Okay, I thought I had it here. Oh, I'll look for it here. Sorry. So yeah, so trying to figure out, okay, once you know what's there, how is it going to be transported? Is it going to be converted to something else? Is it going to be transported? Is it going to be groundwater transportation? Is it going to be some diffusion, absorption, biodegradation, things like this? These are all the things we want to find out. So to do the initial characterization, you need to look at a thorough description of the site, the contaminated site. So as I mentioned, you have to get all of the different characteristics of the site. As I say, it's a very multidisciplinary field, so you need to know what the geology of the site is, the hydrogeology, the chemistry, biology, you know, what microorganisms might be there, what kind of geotechnical characteristics of the soil, all of these type of things to be able to do the complete characterization of the site. So you have to collect a lot of data to find the nature and extent of the site, what kind of characterization. So a lot of these things are done. So first of all, as I was saying, the first part, looking at the scope of the investigation, maybe you want to just try to find out what information, what data is available at this site, as I was saying, in terms of, you know, what has the site been used for? You know, maybe you have some photos of the site. You can get an idea what buildings are there, what potential things have been happening at that site. The second one, to get the extent of the site and subsurface condition, you probably have to start actually physically getting into the thing, taking some samples. So you can get an idea of where the contaminants are, how fast are they moving, where are they going, and this type of thing. And then thirdly, to do a detailed site and subsurface investigation, you might need to do some tests in the lab to see what kind of absorption capability of the soil there is, and these type of things. So yeah, this is the one for surface and water and sediment. You know, like you have a contaminants released into the surface water. You know, try to find out where the contaminants are going, estimate the concentrations, what kind of exchanges there are between the water and the groundwater. Is there a water and surface water expert? Is there potential for need for the water for fishing? is there the potential for contaminant transfer to the groundwater, or to the surface water? How can humans be exposed to this water? And then what other, contaminant mechanisms are going on? So if you want to look at for soil, it's sort of the same type of thing. If you have a release into the soil, where is the soil going? Where's the contaminants going? Is there the potential to reach the groundwater? Is the soil going to be able to support some species that maybe that might affect, like for agricultural purposes and things like this? Are the contaminants volatile, or is there potential for runoff? So all of these are the various mechanisms that you want to look at. And then if it goes into the groundwater, obviously, then you need to know the direction of the groundwater. Where's the groundwater going? Is there the potential to reach humans? Is there the potential for the well water to be used for animals? What other kind of mechanisms that they're going on? What else? And runoff, of course, is it going to go into the lakes and the rivers? Are potential humans going to be impacted by this exposure to the contaminants in the soil, or in the surface water, or the groundwater? These are all the type of things that you want to know. So again, as I was saying, the site background, you need to know what kind of geological information is available. So geological reports, materials, characterization, samples, maybe some air photos. Now we have a lot of satellite data and things like this. You can get a lot of information from that, looking at where where some of the contaminants might be going. Again, so this was the kind of thing. So maybe you want to set up some wells, particularly if it's into the groundwater, to be able to see where the contaminant is going and how fast the contamination is moving in the groundwater. So you have to analyze all the data, see whether it's valid, is it reproducible, do you have enough data, and how sensitive it is in terms of, will you need more data, or is it going to be a waste? So you always have to balance out, like you can always do more wells, but it's going to cost more money. So are you actually gaining more information, or is it redundant information? So you don't really need to do extra wells. So that's always the question. So soil, of course, this needing to know the soil strength, the permeability, the compressibility, all of these are important, because then you can get an idea how fast the contaminants might move through the soil. And of course, the groundwater, where is it going? And you have to analyze the contaminants and what the concentrations are, what kind of contaminants you have. So soil, as I say, porosity, soil structure, all of these type of things are what we want to look at. So we've touched on some of these already. Maybe some of them are not necessarily needed to know, but definitely your hydraulic conductivity is one of the most important ones, because that gives you an idea how fast the water can go through the soil, and hence how fast your contaminants can move. So these are just the permeability testing apparatus that you have. I think it's fairly standard in geotechnical labs. So just to show you a quick calculation, it's just to show you that even if you are sampling, in reality, you're only going to be taking a very small percentage of the soil at that particular site. So if you take 20 samples, each of them are about this size, figure out the volume for each of them. The volume of your site in this particular case is more than 10 to the 6 cubic meters. So then you can see that the volume of the soil that you're actually taking for the analysis is actually quite small. So then there's always a debate of like, what is the most ideal location to take the samples, where to take the samples, how frequently to take the samples, what's the spacing of the samples. So it's always kind of a case by case basis, because sort of every case is very different. So yeah. So what is standard though is how to take the samples, what are the testing procedures, and so on. So like in the US, we tend to use these standard methods for water and wastewater, use EPA methods quite often, ASTM methods for the engineering tests, and so on. And I'm sure other methods are used here in China. No. Okay, so yeah, so you need to have a plan, how to make sure you follow all the health and safety issues. You have to estimate the cost of doing everything, of course, and you have to make sure the data follows all the quality control and assurance methods. So the characterization, as we mentioned, there are both direct and indirect methods that can be used to characterize the site. So the geophysical methods can be used to look at the subsurface. So these are what we call indirect methods, because they don't give you specific information, but they kind of imply what's there. So looking at using, like for example, for resistivity, looking at using the electrical current, passing electrical current through the soil, see what kind of characterizations and feedback you get. And you can get an idea of what kind of materials you have, what kind of porosity, the water content, and the concentration of contaminants in the pore water. So basically very indirect methods, as opposed to taking the sample, analyzing it, and knowing exactly what the... So it can give you, you have different methods that can give you the aquifer, looking at the water table, the bedrock, the soil type, and what kind of contamination you have. So this gives you an idea, like you get the measurements of resistivity, you have your spacing of your electrodes, the voltage, the measured voltage, and the current that you do. So basically, whoops, there's a bit of a glitch with the diagram here, but anyway, that should be the S, is basically the spacing between the electrodes there, and you have your measurements and so on. So that can give you an idea. Seismic waves are another way that you can look at. Basically, you introduce energy pulse into the soil and you get a kind of a reading. And the advantage of this method is that it can give you an idea of how deep it is to the bedrock to do these type of analysis, when you do this type of analysis. So basically, so this is the idea: is you hit a source, it's a metal there, basically it's like a hammer, you hit it, it creates these waves, and then you have these geophones on the surface there, and then you wait to see what kind of delay of response that you get. And so based on this bounce back from the rock, you can get an idea of how deep the surface is to the rock itself. So that's basically the idea of using the seismic waves. You can use electromagnetic waves. It's also another way to look at the geochemistry into the groundwater. And so you can get an idea if there's something different in the soil, and get an idea then if there's some groundwater contamination. You could use radar, ground penetrating radar. Again, it's kind of a reflective wave type of thing. You look at the sonar profiling, and you can detect all sorts of things like voids in the soil, trenches, plastic or metal buried drums. So you can all do all of these types of floating hydrocarbons and things like this, and these things can be detected without actually having to drill down and find the drum. Yeah, so this is the seismic one that I mentioned before. So basically you get a velocity, and then when you see the change, you get an idea of what's the distance to the bedrock. You could do magnetometers. This shows various anomalies in the surface as well, and so that also can show whether there's some hydrocarbon contamination or something like this. So it gives you a different signal when there's water compared to hydrocarbons. So obviously, to be able to interpret it, you have to have very skilled people to look at these type of things. So you can see here that there's some contamination because it's quite different compared to the rest of the areas. So again, here's the ground penetrating radar. There's a gasoline tank in this particular thing. So basically the radar will bounce back on something metallic in the subsurface. So things that are like drums and power lines and all sorts of things that are, that are not usually found in the ground can be detected. So these are initially, as I mentioned, these are indirect methods. So they don't directly tell you like what's the concentration of a contaminant and so on. Oops, I'm going in the wrong direction here for a second. So you need to actually do as the next step. Most likely what you'll have to when you get an idea of sort of where the contaminants are and so on, and to get a more explicit idea, you need to do the boring, sampling, and testing to be able to see where the actual contamination levels are and what is exact contamination levels and what are the contaminants exactly there. So all the methods I just mentioned before are very indirect. They can give you an idea that there's something there, but not exactly. So, but to get an exact idea, obviously you have to do the monitoring either through the groundwater wells or some soil sampling. So each of these techniques has their limits and so on. So you can have various there are different types of soil drilling methods to get the samples from the soil. So depending on how big samples that you want and so on, you can measure these type of things. So they're all different types of things. So you can have drilling methods like this one. So these are the type of things. So basically like a little bit of a drill, really. That's exactly what it looks like. And so you can get the soil samples from the drill bits, basically, and you can extract the soil this way. So these rotary methods are very old, used a long period of time, used for unconsolidated sediments and soils and so on. And so you need a bit of a drilling fluid, obviously, to help to loosen it up. And you could use air as well to do these drilling. So just make sure that you don't do any cross-contamination when you're doing the type of thing. This is like a mud rotary drilling apparatus. So these are, you can get all the samplings here. Basically, you have your drill bit and basically you carry up the soil or sediment samples this way through the drilling materials. So, so these other tests can be also done in situ. So these standard penetration tests are more geotechnical type of testing, looking at the soil type of compression tests and things like this. Whereas you have a hammer basically that falls down and you see how many hammer blows it takes to move the peg a certain amount. So that can give you an idea of the density and the strength of your materials. You have the cone penetrometer test, which gives you an idea of the soil strength. You could also put a piezometer as well to measure the pore water pressures as well. And you could also add various detectors onto it that could also be used to do some analysis for various hydrocarbons as well. So this gives you an idea of the cone penetrometer testing. Basically, you have the truck, which basically shoves this tubing into the thing, the sensor at the end of the tip here, and it gives you these readings of the resistance. And as I mentioned, you could put other types of sensors on the end, such as this laser-induced fluorescence sensor, and it can give you an idea of how much hydrocarbon is there. So there are other types of shear strength methods, looking at the vein shear test. Basically, you stick a vein into the thing and you turn it and see what kind of resistance there is, and that gives you an idea of the strength of the soil. So that's the diagram of what the vein shear strength looks like. You have these dilatometer tests also that give you an idea. Basically, it's a membrane that you inflate and you see what kind of resistance there is to the membrane that gives you an idea of the earth pressure. So that's the idea. You stick it into the ground and basically you inflate it, and then you see what kind of resistance there is. And then there are other types of tests as well, these pressurometer tests. You could do these in situ water level tests because you need to know where the groundwater level is, basically, quite often. So this will give you an idea where the groundwater level is to do that. The in situ hydraulic conductivity tests is also just do an infiltration test. You can see how long it takes for a particular component to pass through the soil. And you can do some in situ water quality things there. So this is very fiber optic methods to measure the mercury, chromium, phenol, and I'm sure a wide variety of other methods as well at this point. So soil sampling is not easy. So if you get the cuttings, it's not easy to determine exactly where you got the sample from. So really it's called the disturbed soil sample when you're getting it, because really it's not as it was in the soil itself, right? You can also get some undisturbed samples by doing these thin wall samplers. So basically you take a core of the sample of the soil, and it gives you a bit better idea of the soil as is. So it's called undisturbed sample, but in reality it's kind of the least disturbed sample, because it's you know, you're still doing some changes, because once you're taking the sample, it's not going to stay as it was initially. So these are some core samplers that you can have a look at. So you can also take samples of the rock. The rock, of course, is obviously much on the, like for the bedrock underneath, and gives you the type of bedrock, how much voids, fractures, things like this, and it gives you an idea of the rock quality. So these are, of course, are very difficult to obtain because rock is very hard. So often you need these diamond tips and things like this to be able to get the samples of the rock. So for the water level, as I say, you tend to use these pressure head using these piezometers, so they'll give you an idea where the water table is and how to where the water is located. So you can get, as I say, an unconfined water table, which is the normal situation. But what can also happen is that you can have a water table kind of plunk in the middle, and it's not a continuous water thing. So you could get a little bit fooled by when you go down, you do your sample and you go like, hey, I've reached water, but maybe that's not the actual water table. And then you keep going down, you'll find the actual water table, as you can see in this continuum. So the subsurface is a little bit confusing sometimes. And then, of course, you can do geographic information systems to try to give you an idea of where and how things are spatially put together and where the location of various stuff is. So to give you an idea, just to show the different rock layers, this is clean, this is contaminated, this contains this levels or whatever. So obviously this is not in color, but you can have a very good way to look at and get a better visual idea of the contamination levels. So in reality, you need to obviously take a lot of data. You need to, as the first estimate, try to figure out where the concentrations are, what kind of risk you're dealing with. And then on the second one, you have to look at what kind of receptors, what kind of risk you have of the contaminants at that particular site. Where is it going to be moving to? And then what is the, you know, where potentially could these contaminants be going? And then finally, you're going to have to make a decision if there's remediation that's needed, what type of cleanup that you're going to need, and you know, basically looking at you know, you're going to have to identify all of the all the levels of contamination, decontamination that you're going to need, and then you'll have to obviously come up with different options for the remediation. So what are you going to do with the remediation? How are you going to go about it? What kind of options are you going to be considering? And hopefully you'll choose the more sustainable one as much as possible. So obviously there are a lot of challenges for dealing with remediation and contaminated sites. So you want to make sure that you extract the non-renewable resources as sustainably as possible. Various activities, of course, generate various contaminants, and we want to be able to have good places that are safe to construct habitats for humans, obviously. So you want to make sure that you preserve the geoenvironment, both the water and the groundwater sources, and the soil as well, because you also want to make sure that the habitat is protected for the animals and ensure the biodiversity in the area as well. Yeah, so all of these type of things are sort of things that you are the unsustainable part. Too much contamination, too much waste, too much effluents going into the water, too much destruction of habitats, too much discharges of contaminants. And then we would like to be much more, resource conservation by reusing, recycling, treating the groundwater, soil, doing better agricultural practices, and doing doing treatment processes to neutralize your contaminants. So yeah, so there are a lot of evidences of very unsustainable practices. We've had many accidents, oil spills. We had a major accident in Quebec a long time ago called the Lac Mégantic, whereas a train was kind of run off. It's a guy who was operating the train. He parked the train on a hill, thought he put the brakes on, and then left for the night. The next morning, or during the night, the train rolled down the hill, and it it derailed and ran off the rails there, and basically it was carrying a lot of very hazardous oils and things like this in tankers. These tankers exploded, and there was a fire. About half the town was destroyed. There were about more than 70 people were killed, and more than half the town was totally demolished, just because of the, there are many procedures were not followed properly. Yeah. So that's basically contamination, things like that. Okay. Yeah. So that's definitely not a good thing. Hopefully a little more sustainable side. These are some examples, whereas you have a coal mine in Germany, and there was some washing. The coal mine closed in 1978. You had a lot of contaminated land. The land was starting to, there was subsidence. It was starting to collapse a little bit because of all the underground work there. There wasn't the proper ground procedures underneath and supporting properly. You had the acid mine drainage. You had gases due to from the coal procedures. So you had methane gas that was leaking. And you had a lot of underground structures, tunnels, all sorts of stuff. So the Ministry of Academy decided they wanted to redo the place there. They set up a whole. They regenerated the area. They developed a bunch of shops, housing areas, and so on, a conference space, hotel, restaurants, and so on, and a recreational park. So eventually, you had the increased land space. They used a lot of solar. They captured the methane gas to use as a energy source. They reused the water in the area, and then they remediated the contaminated soil. And they used a lot of liners and membranes to control the contamination in the area. So it's kind of what it looks like. So they put in some, they did a lot of controls of the old waste site, and then they put in some newer buildings, as you see on this side. So this is another site, was an old petroleum refinery, whereas they took all the piping and all the concrete for reuse. They recycled all of this stuff. They recovered the groundwater. They did a lot of aeration and so on, and then they redid the whole area and made it like a golf course. And then they hid some of the water treatment facilities as kind of nice wetlands and things like this. So they had some nice little ponds or whatever that were in reality the treatment for the water at the site. So yeah, and then other types of sustainable practices looking at reusing contaminated glass and things like this. This glass earth is actually the what do you call it? Vitrified soil that was contaminated, and they were able to use it for many different purposes later on. And it's well, okay. And this is another case in terms of sustainability, looking at the port of New York, where they had some contaminated sediments. They ended up reusing these contaminated sediments for as a foundation for parking lots. They dredged the sediment, transported it, screened it, and mixed it with some kiln dust to do the remediation. So I think I will leave it at that for our break. Yeah, I'll leave it at that for the break. Anybody still awake?
Things are getting more and more detailed.
Yeah. Some more on urban waste management this section. And then, so a lot of geoenvironmental engineers do a lot of landfill, stuff.
All right. We can discuss on that. Oh my gosh. Oh, this is the next. See this one. This one. Based on hydrogen.
Yeah.
So
yeah, there's one graph. Little slides later. shows you kind of the readings you actually get.
The there is a tree that's so
Yeah. So
I remember.
wait, this one.
Yeah,
This one, yeah.
There.
So this would be like the normal reading that you would get like over time, and then you would see like a shift because of the bouncing from the. So then you would start to see a different curve.
But I just wondering the distance, right? This distance and the time.
Yeah, so you will get some kind of obviously the normal readings because you will have the thing there. So it hasn't hit the bedrock yet, but once it does hit the bedrock, then you'll start getting a bit of a shift.
I was wondering how can we can share the slides.
Yeah. Okay, thank you very much. Okay, we're back again. Noisy. I'll wake everybody up. All right, so looking at, so this one is a little bit on waste management for the urban area, sort of, and looking at some of the land uses and so on in an urban area. So just in general, land is used for many purposes in an urban area. So you can use it for parks, you can use it for roads, you can use it for buildings, all sorts of things. And of course, we have contamination in these areas. So many cities, when they're building up cities, of course, they will, to build the buildings, you clear the forests and things like this. So you lose a lot of these wetland and forest areas due to construction of cities. So in the US, it's quite a large rate of loss of land like this compared to Europe and, well, where they did a lot of construction a long time ago. And so now the newer construction is not so much. So in an urban area, of course, you're going to have contaminants, many types of contaminants. You have all the buildings that give off carbon dioxide. You have the fuel, the cars and so on. I mean, the electric, of course, are better, but still you have some cars with fuels that are burning fuels and so on. So they will give off all sorts of particulates and carbon dioxide and so on. You generate liquid like wastewater, solid waste that go to the landfill. And of course, you can have runoffs from paved surfaces and so on, which can go into streams and rivers. So if you have the roads or whatever, you have all of the tire residues and things like this, the oils and so on, the you know, like that are used for all certain things. So all of these are different types of contaminations in an urban environment. So the soil, as I said, is used for many different things, for, you know, for as a support for buildings, for plants, for erosion and runoff uses. So obviously you can impact the water quality based on all of these runoffs. You have the leakage from sewers and so on. You have excessive groundwater extraction sometimes, and the wastewater discharges. So this is just a case of excessive groundwater extraction. So you can see that it's cracked the foundation of this building, and they had to extend the support for this for this building because of the ground was settling due to the amount of excessive groundwater that had been taken in this particular area. So landfills, of course, are a means of dealing with the waste that's generated in an urban area. So you can have incineration that can be also generate some residues as well. But so you will, regardless, you'll still need to have a place to get rid of your waste materials. So yeah, you have, as I mentioned, raw sewage, you have wastewater treatments, and so on. So yeah, you have many also industries within an urban area. So things like laundries, printing facilities, railway yards, sewage treatments, battery recycling, airports, and things like this. And each of them have their own issues with soil contamination. So depending on what will happen. So like especially in Canada, where you have very cold weather. So in the winter, you have to do the de-icing of the plains. So you have to have a very controlled area where you do the de-icing so that you can collect all of these glycols and things like this that are used for the de-icing procedures. Just as an example. So this is just something that we did in a backyard of somebody, and we found very high levels of zinc. I think in this particular case, it had probably been used in the past as a bit of a dumping area for waste. This is a case in one of the Japanese islands there where they had, it's sort of very similar to the case of the Love Canal that I had mentioned in the US, whereas they had this island basically that an industrial company was using as a bit of a dumping area, and so the citizens in the area were being impacted by this dump. And so after a lot of documentation and showing that eventually that they were getting sick because of the contaminants in this area, they eventually agreed to do the cleanup in this area. So what they did was they first of all built a wall to protect the citizens from further contaminants there, and then they eventually did the decontamination of all the solvent drums and everything at that particular site. So you see that it was getting to some extent some of the contaminants into the groundwater. There were some into the surface water, and some of it was just leaching from this contamination. You can have building materials also that could have leachates coming from them. And also you can have wastewater solids that are generated from wastewater treatment plant that do absorb a lot of heavy metal contamination as well. So you could reuse some scrap tires and things like this in different areas. So sometimes they've been used in landfills and so on as a cover and so on, and then used maybe for various what do you call construction areas, maybe looking at a track like for athletic purposes, maybe in particular parks and things like this, using different parts of the tires. I'll leave that. Anyway, so as I've kind of mentioned, I think in the past, so to do the investigation of a site, you need to do that first. So you can use some of the procedures which I just mentioned before the break, determine if the site is contaminated. If it is, then you have to go about trying to figure out where you'll do the decontamination, try to figure out what kind of options that you would need to do the decontamination at that site. Try to choose the best option, obviously, evaluate the risks of doing the various options, see which one might be the better, which one might be the most cost effective, sustainable, and so on. And then hopefully you'll be able to do the decontamination to the levels that are required through regulations. So in the US, it tends to be a risk-based evaluation that's usually done, and they decide what level of contamination that you would need to get to. In Canada, often it's very prescribed. So like in my province of Quebec, we have various levels depending on what kind of use would be the soil for. So if you're going to use the soil for residential use, you'll have a certain level of contamination levels that you have to respect. If it's going to be used for commercial purposes, or if it's going to be used for industrial purposes. So depending on what is going to be the use of that land, then that's what the levels would be prescribed for the decontamination that you would need to do. So yeah, so hopefully you reuse lands that are already contaminated to be able to reuse to have a more sustainable land use, instead of going to a green area, cutting down the trees, deforesting the area, and so on. It's much better to try to reuse an area that's already been deforested and so on. Try to do it. Sometimes it's a little bit more complicated because you have more regulations. It costs sometimes more in terms of doing the decontamination, but definitely it's a much more sustainable approach. Sorry. So yeah, so we've just kind of mentioned sustainability. I think I mentioned this before, probably yesterday, in terms of looking at various indicators for evaluating sustainability, and that even goes towards what remediation technique that you're going to use. So how much water you're going to use, how much energy will you use, how are you going to be recycling your water, and so on and so on. So yeah, so these are some indicators for sustainability in terms of greenhouse gas emissions, energy aspects, how is it going to be affecting the climate, and so on and so on. So yeah, so you can put various barriers, as we've mentioned, the vertical barriers before for the groundwater control. You could also put a horizontal barrier like underneath a landfill if the landfill happens to be leaking. This might be an approach that might be necessary to protect the groundwater. Okay. So traditionally, you have the landfill. It rains, the water goes through the landfill. You have the leachates produced in the landfill. You recover the leach. Sorry. But people have been looking at developing a new approach to landfills and trying to develop the landfill as a bioreactor. So in this way, so normal landfills are very dry, and that's the whole aspect. What you're trying to do is keep the landfill as dry as possible. Whereas in this case, what you do is you collect the landfill leachate, and then you re-inject the leachate into the landfill so that you increase actually the moisture content of the waste in the landfill. And this way, you would be producing, you keep it a bit more moist, and the idea is to have the bacteria to be a bit more active in the landfill, and so that you would be producing more gas as opposed to what you would normally have in a landfill. And the advantage of speeding up the degradation means that you could probably put more waste into the landfill over time compared to a normal landfill, because now you're speeding up the degradation time in the landfill. So this is an approach that some people are using, like some experimental landfills in Calgary and so on. They've set up this way. So you just have to make sure that you collect all the landfill leachate very well. That's basically, you don't want to have too leaky a landfill, or else this is not going to work. So as I mentioned, this is kind of the normal landfill. You have your landfill, you have your membranes, hopefully underneath there, the geomembranes and so on, and then you'll have a clay layer underneath to be able to attenuate the pollutants underneath the landfill. So this is an ideal setup of a landfill. And this is all what we call this engineered barrier system here. And then of course you have the monitoring wells to see whether you're contaminating the groundwater or not. So yeah, so you want to make sure. So the idea is if you're using a engineered liner underneath the landfill, you want to make sure that the permeability of that layer is very, very low. So you have to usually respect something like permeability of 10 to the minus 7 centimeters per second, something like this. It's very, very, very low. And you would use a clay like montmorillonite that is a swelling clay that has a lot of absorption capabilities as well. So these are ideally what you would want to have underneath the landfill. You want to have very good absorption capability, and you want to have low flow coming from your landfill. Oops, sorry. Yeah. Buried structures. Anyway, this is kind of this is actually a site in Montreal, the east end of Montreal, where they receive contaminated soils. The soils must be organically contaminated. Sorry. So like usually an oil contamination or something like this. And so the basis of this process is to use the bacteria in the soil to do the degradation of the contaminants in the soil. And so basically it's they pile it up make sure there's enough airflow, and they inject air into these piles. It's a process where they can treat these oil contaminated soils. And I think we had some discussion yesterday, but definitely this is a summer type of process. You definitely can't do this in the winter very much in Canada in particular, because the bacteria don't work too well. Actually, your soil is totally frozen. So this is a process that is done usually within during the summer months. And usually it takes maybe, I think maybe a couple of months to do the treatment this way. So, yeah, anyway, I will skip that. Yeah, so these are just some landfills that I've visited in different countries, actually. I don't remember where this picture is from, but this is from France, for sure. This is basically the lovely smells of a landfill. Really, but as you see, this area where the poppies are growing, it's a covered. Basically, they cover it over after the landfill is completely full, and so that's the waste is underneath this area, and so now they've just allowed the greenery to cover the landfill. So yeah, so this again is in France. Here they're recovering the gases, the biogases that are produced during the degradation of the waste in the landfill. And so what they do is they recover the gases from the landfill. They pull out, so they cover it. They put various membranes on the top of the landfill, and they make sure there's no leaks and so on. And the idea is that you pull out the gas that's being produced in the landfill itself, and you bring it to this generator, and you remove the moisture, and they try to produce. So basically, from the methane, they will generate energy, which could be used at the site or for the community around, or so on. So yeah, so these are basically what some of the old procedures looked like for dealing with landfill waste, just people just dumping anything anywhere. And of course, in some countries, that's where it's still done. This is a closed landfill in Canada. Basically, now they've repurposed it now as a golf course, and so you would never know, obviously, that there's a landfill underneath it. Yeah, so repurposing landfills is good, but make sure that you don't put buildings on top of it, because you'll still have settling of the waste and things like this. So, and potentially you might have infiltrations of methane gas into the house and things like this. So into the building. So definitely putting buildings is not a good procedure, but other things like parks and golf courses and things like this are good ways to redo old landfills. So this is one in South Korea, I think, if I remember correctly. As you see, this is the where they're extracting the gas from the landfill. This was an old landfill that they had before they redid it. So I can see this styrene and things like this that don't degrade, doesn't degrade very well. You can still, this is probably a 40, 50-year-old landfill. And you can see the plastics and the styrene that obviously doesn't degrade over time. It just stays there. So this landfill was not designed properly. You can see that there's a waterway right here. So this is not how you would do a landfill. Because even here you can see that the groundwater is into the landfill. That you don't want to happen, because you don't want to be contaminating your groundwater. And this is what exactly that was done. So what actually they ended up doing there, because this was they wanted to do a development of an area. So what they actually ended up doing is removing that whole landfill and repurposed the land, brought new soil in, and built like a shopping center and some housing area and things like this. So because like in places like Korea, it's like land is very very scarce. So that's what they did. They ended up doing repurposing that whole land area. So yeah, so I did this, and this, yeah. Anyway, so just to, as the quick joke, is here's not how to dress when you go to a landfill visit. They told me, oh, let's do this lecture. You can do this in half an hour, but first of all, we will go to the landfill before you do the lecture. And as you can see, my shoes are very dirty. Yeah, so that was not a good. I had to go clean up my shoes entirely because they were just, because it had rained the day before too. It was just such a mess. Anyway, so yeah, so this is, as I say, before and after in a French landfill. So yeah, there's ways to repurpose landfills. So you have both hazardous waste landfills and municipal waste landfills. So there are two different ways that the landfills are developed. The hazardous waste landfills obviously have to be much more designed carefully because it's hazardous waste. So usually you will have two sets of liners, two sets of leachate collection systems, and so on. So to be able to protect the groundwater even better. Many countries use incineration as a way of dealing with the landfill, the waste. So since I mean, I spend a lot of time in Japan, so that's why I always giving Japan examples. So they really don't have regular municipal landfills. What they do is they have places to put the waste, the ash of the incinerators. So basically they incinerate all of the waste. And so all you have left now is a very small volume of waste. So you just have the ash, and then they just have to dispose of the ash in a landfill. And so they from the doing the incineration as well. So this is a landfill that was built near Kyoto. And so this was the liners that they have there, and basically they deposit only ash in this landfill. So they just have to protect it just from the ash. So in the ash, of course, you will still have concentrations of heavy metals and so on. All the organics are pretty much destroyed in the incineration, but you might still have some heavy metals in the ash as well. So there's still the potential of leaching of materials from the ash. So that's why you still have to have a really good liner system, as seen here, even though it's only ash. So yeah, so that's just a hazardous landfill basically. You have a daily cover, you have the soil that you put on top basically to minimize the transport of contaminants. And then you have some, they put some soil on the top each day that you bring the waste in. So this is actually a hazardous waste landfill because it's got like double the leachate collection systems, double the liner systems, and then you have the compacted liner. So this is obviously for a hazardous waste landfill. So many different countries have all sorts of different rules. Europe has different rules from North America and so on. So you can put all sorts of different combinations of geomembranes, geotextiles, various types of collection systems, clay layers underneath. So basically you have to follow the regulations in that particular region that you're in. Yeah. So as I mentioned, all different combinations are possible depending on where you're at. So where to put a landfill is usually a hot potato issue because nobody wants a landfill anywhere near them. It smells. It's you have a lot of traffic going in and out with the trucks and so on. So nobody really wants these landfills. You also have to have the correct geology, hydrogeology, and everything near the site. You don't want to have underneath a leaky area. Ideally, you want to have a clay layer underneath your landfill. And you must not have the runoff going into rivers and lakes nearby. You must not have protected areas nearby as well. So yeah, so there are all sorts of liners that are used. None of them are 100%. There will always be little perforations. And so you have to have all sorts of backup systems to deal with these perforations. Yeah, so you have to deal with the leachates that are coming from the waste. This will pass through the filters, the geotextiles and membranes and things like this due to the advection because of the water coming through the landfill. And you will also have some diffusion as well. Yeah, so I don't know. Yeah, so basically you'll have this transport of contaminants through your landfill liners. So basically you want to have a very low conductivity system and high absorption. That's basically what you want underneath your landfill. The cover on the end, it's sort of the opposite. I mean, well, you want to deal with everything for the final cover. So you want to have water control. You want to control any animals that could get into the thing. You want to control the gases. So you don't want to have leaking gases into the air. And you want to prevent erosion and minimize the odor. So those are what you're trying to accomplish by the cover systems. So yeah, so you can have, these are an indication, sort of you have your waste, you put some soil, you put some gas collection layers, you put some other types of barriers on your styles, and then you could put some soil like in France. So that's a type of system that you can use. Yeah. Yeah, so basically you put all sorts of membranes, geomembranes through it. There are all sorts of properties, and you use what you need for the particular purpose. I don't know, I don't really want to go through the geotextiles. This is not a course on geotextiles. So yeah. So yeah, you will have some geotextiles, geomembranes, and all things. So you need to have the appropriate one that you will choose for your systems. So bentonite, as we mentioned, is the best clay to have underneath your soil because you have high cation exchange capacity. You can exchange the ions with the metals that are coming from the waste. It will absorb a lot of the contaminants, such as the heavy metals from your waste that are coming through the leachate. You will have a certain amount of diffusion that's going on, but as I say, because of the properties of the bentonite, you will have a very low hydraulic conductivity and very high absorption capability, so it forms an excellent layer for your contaminants underneath your land. So yeah, so you can have a certain amount of transport, as I mentioned, through these liners, through advection and diffusion. And yeah, so the diffusion, so this is kind of the quick rate of diffusion that you can have, this fixed layer. So you have a diffusion coefficient, you have this retardation due to the absorption, and then you have basically the change of concentrations from distance and so on. So this is basically your change of concentration over time due to diffusion. So your retardation, as we mentioned, is basically dependent on the porosity of your soil and your capability to absorb. So this KD, as we mentioned a long time ago, I think at the beginning of this course, was basically this capability of your soil, and in this case, the bentonite. Yeah. So as you see, the percentage of the bentonite, your porosity will change, and your bulk density will change over depending on what percentage you use. And you see that the KD will increase as you increase the thing here. But as you see, there's a bit of here in terms of maximize the retardation, because that's basically what you're trying to do. So the ultimate percentage of bentonite that you would like to use is going to be approximately about 10%. Bentonite will give you the optimal absorption capabilities. Yeah. So yeah, so you can get some transport through the clay, but because you're going to have a very low hydraulic conductivity, it's going to be very slow. So because it's in the vertical direction, we look at it in terms of the hydraulic gradient, in terms of the depth over the clay liner, and then, so this is your height, and your thickness will be the clay layer. So that will be the two things that you can be used to calculate the hydraulic conductivity, the hydraulic gradient. And as I say, you'll like as before, you'll multiply it by the permeability, and then you can calculate plus. So this will give you your contaminant transport through a clay liner. So it should not be very extensive, as you can see, depending on, I mean, these are using different types of clays and things like this. And you can see with an eelite and things like this, that smectite and so on, you have very low conductivities. Yeah. So I think I'm pretty much done with this set of slides. Yeah, so this just kind of shows a sustainable management approach for waste. This particular is looking at agricultural waste. Sorry. So in this case, you have your cows that produce the manure. You can do the anaerobic digestion. You can get energy from the anaerobic digestion. You have the compost that's also produced on the wet side, so you can use the compost for fertilizer. And then you can get electricity from the biogas, and you can use the sort of like the wetland ponds for treatment of the water part. So it's kind of a very integrated management thing, and you could sort of manage to do the same type of thing maybe for urban waste as well, because you can do digestions before you're sending it to the landfill. Now we do a lot of composting and things like this in North America. So you use the organic materials. So it's an approach now to remove a lot of the organic materials before it goes to the landfill. Of course, that way you decrease the amount of gas that's being produced. So it has its pros and cons. So if you have a good system that you're actually recovering the gas from, it's probably not the best procedure to remove the organic materials before sending it to the landfill. But if you don't have a biogas system on your landfill, it is the organic materials are the best things to remove, because you'll be producing lots of gas and things like this. And if you don't have the capability to recuperate the gas and the electricity, it's probably best to minimize the production of your biogas. So I think, yeah, that's the end of that set. So, hey? Yeah, I went a little bit faster on this. So I can do two things. I can stop now. Now we have maybe an hour left anyway. Or I can go a little bit more. What did I have not done? I haven't done 8 and 7 and 5. There's no 7. No, I don't have the 7A. I didn't copy it here. Oh boy. I was supposed to copy it on here. Okay, so the 8 and 7. So the 6. Let's see, did I put 6? Yeah, I put 6 here. Okay, 6 I already did. Okay, that's done. So 8 and 9. And 9. Okay, so 8 and 9 are the last two, I think. Yeah. Yeah, so 8 and 9 are the last two.
I think these two should be enough for the next hour.
Yeah, because I have this one I will go through quickly. So this one is only 44 slides here, so I could do this one quickly. So So I can do half of this one, maybe. Yeah, yeah, and then we'll finish. Yeah, I could do that. Yeah, I don't remember what 7. Maybe I have to look on my. Oh, I know what 7 is. 9, 7. Actually, I should do 7. I might do 7 instead of. Yeah, I have to get it from my computer. Yeah, I'll have to get it from my computer. So it's a good thing I brought it. Yeah, okay. So we'll do that. I'll get that file. Yeah. All right, so we'll do this in Okay, good. So we come to the last part of this course. So hopefully everybody is still surviving here. Okay, so it's kind of a bit of a long day. Okay, so I'm going to give kind of a very brief overview of a lot of different remediation techniques. So that's kind of the theme of the last piece here. So I'll start with these physical chemical ones. So a couple of them I kind of briefly mentioned already, the soil vapor extraction, chemical oxidation I haven't mentioned, the flushing and soil washing I mentioned a little bit already, but anyway, we'll mention the other ones. So in general, you have remediation techniques that are usually divided two ways, in situ and ex situ. So in situ means at the site, you do the remediation at the site. You're not transporting soil anywhere. You're doing everything directly at the site. Whereas the ex situ, basically, it's kind of known as the old dig and dump, basically. So you take out the soil, bring it somewhere else. You could be just depositing it at a landfill, so basically hence the dump part. Or else you could be doing another remediation technique before you're bringing it to the landfill. Because maybe the landfill operators don't allow you to bring such hazardous waste to the landfill. So you have these excavation, as I say, you have these ex situ techniques. So the excavation is always the first part. So you can do soil wash, solidification, or biological treatment, or you could do washing. This actually should be two bullet points. The in situ bioremediation, air stripping, thermal treatment, extractions, chemical treatments, solidification, stabilization are all some of the common techniques that are used. So which method depends really a lot on the contaminant that you want to treat. So whatever the contaminant properties are. So as I've mentioned, you do all the soil characterization, the site characterization, identify which techniques could be used, compare your risks, develop the methodology, execute your remediation, do your monitoring, and hopefully at the end of it, you'll achieve your goals for remediation. If not, you have to go back to the drawing board and try again and use another technique, and hopefully you will have a good remediation at the end of that. And so once you eventually get your remediation, you achieve your clean soil. So as I mentioned, you could do physical. So the isolation basically is just a kind of a stopgap method. As we've mentioned before, basically you're just isolating it. You're not really doing anything. But what you could do is like do the isolation and then excavate it and bring the soil somewhere else eventually. So you could do, once you do the extractions, you could do some physical separations. So there are a whole set of techniques. A lot of them are used like in the mining industry. So when you're processing mining ores and things like this, so a lot of these processes are available for the mining industry. So they're well known. And so the idea is to try to reduce the amount of soil that you need to contaminate. So you can remove some of the larger particles. So things like rocks, gravel, things like this are not really contaminated. So you can remove this fraction, and then you will have what's left of the soil. You can do the treatment on that, and it will cost you less money because you have less soil to treat. It basically involves passing air through the soil, and you want to make sure that it can only be used for volatile contaminants. So things that are easily extracted by volatility. So this is the thing: you pass the air, you get the contaminants that go into the air, and then you can treat the air, as we've mentioned before. So you devise it in terms of the pressures and whatever, and you developed a certain amount of well spacing and things like this. So you can calculate all of these things based on unknown design things. So you do need a high conductivity of the soil, and you also need a high volatility of your contaminants. Yeah. So, so basically you're doing advection and a bit of diffusion to be able to have the contaminants to move. Yeah, so most of the movement is by the advection, and so you do have a bit of diffusion that does occur. So the Fick's law, which I've mentioned before, you can do the calculations for diffusion. The Henry's law is kind of, which I haven't mentioned here, but it's basically the way of knowing whether your contaminant is volatile or not. So again, the equipment's well known. It's you don't need to add anything. You're just adding air or pulling air through the system, and basically it's kind of a fairly popular method. Sorry. So you need a high permeability soil. You need a high volatile contaminants and fairly low groundwater levels. So this is blurry, but this gives you an idea. If your contaminant plume looks something like this, you could set up about 4 different wells and do the soil vapor extractions at these 4 different wells and be able to cover most of the area that's covered by the plume. So air sparging is kind of on the same principle, but it focuses on the contaminants in the groundwater. So the idea is to blow air into the groundwater. And so again, you would volatilize the contaminants from the groundwater. So again, it is applicable for very volatile contaminants and can also be used in the groundwater as opposed to the soil vapor extraction, which is just in the soil itself. So looking at the geology, the hydrogeology, all of these things you need to know to be able to design your system. Again, fairly low operating and maintenance costs. Whoops. And most things work pretty, as I say, you focus on volatile contaminants in the groundwater this way. Horizontal wells can also be used. And you can also, if required, do some fracturing. This is probably not highly recommended, but it is possible if you find that you're having difficulty removing some contaminants from a clay or a shale or something like this. The soil flushing, as we've mentioned before, you're injecting solutions into the soil to allow the contaminant to move via solubility with the water, and then you would recover the contaminants by these recovery wells on the other side. So you could add various solutions to increase the solubility of your contaminant, whether it be surfactant, acid, base, solvent, steam even, to increase the solubility. So again, you need to understand the hydrogeology. It's most applicable for highly permeable soils, and really applicable for soluble contaminants. Yeah, I won't go into all of these little details there, but basically, yeah. So solubility is the key. There are different ways you can add the solutions. Basically, you can do infiltration, you can do injection, you can do leaching fields. There are all sorts of different ways you can add the solutions to the soil to target where the contamination is, and then to try to recover the contaminations via the wells. So again, you need a highly permeable soil to do this type of work. So soil washing is the ex situ process of the washing. So you've actually excavated the soil, bring it somewhere else, add the solutions as similar to what we did for the soil flushing. But the idea is that you can control things much more easily, because now you can control all the liquids and easily treat the contaminant liquids and so on. It's obviously much more expensive because you're doing the excavation and then you're doing the treatments, but you do have a lot more control over the situation. So this gives you an idea of some of the things you might want to remove some of the larger particles first, You can do some mixing with cyclones and add some stuff. You can do all sorts of things, but as I mentioned, you can control and and separate your solids and liquids and so on, and do the treatments that are necessary for the soil. And hopefully you have very good soil treatment this way, and you can treat also the liquids. So you could also do chemical oxidations for organic contaminants, things like ozone, peroxide, chlorines, fenton agents, things like this could be used. So this can be done either in situ or ex situ. You could directly inject these type of solutions into the soil, or you could excavate the soil and do these treatments the other way. So yeah, ozone is, you have to make some control of this. Hydrogen peroxide could be used, and there are other types of agents also could be used. So basically you're breaking apart the organic contaminants by adding these chemicals. You could also do nanomaterials. These are kind of becoming much more popular and kind of the in thing, because you have very small particles which can be allowed to percolate through the soil because of the small particle size, 10 to 100 nanometers in size. So you should be able to get the particles to where the contaminants are, but then there could be some movement of these nanoparticles to other places, maybe that you don't want them to go, and maybe they can accumulate in some organisms and things like this, which you really don't want to have. So at this time, the electrokinetics, we mentioned that before, and yeah, so that's that set of slides. So as I mentioned, that was quick. Okay. So let me do the bio first, and then I'll do the stabilization. Okay, so the bio. Okay, I'll try to go through this relatively quickly. So bioremediation is another type of remediations that you want to do. So the whole idea is that you're allowing the microorganisms that are in the soil to do the treatment for you. So they're doing all of the work basically for you. So they're the workhorse. So you can have fungus, plants, and things like this. They're kind of the bacteria are at the bottom of the scale here, but they're the most useful, and those are what would actually do the work in bioremediation, the bacteria that are in the soil. So to know whether bioremediation is feasible, you need to know what type of contaminant you have and whether it's biodegradable or not. If it's not biodegradable, this is not a good technique. If the soil characteristics are not good, also if it's not permeable enough or whatever, it also won't be working here. So yeah, so it depends, as I say, on the, so you can kind of get an idea whether something is biodegradable or not by the structure of the compound. So if there are a lot of chlorine groups, or the molecule is very large, or if there's very low solubility, that compound, or if it's very hydrophobic, these are indicators it's probably not very biodegradable. So otherwise, so I mean, that's just an idea. It shows you. So if it has a half-life of 15 days, it means that 50% of the product will degrade in 15 days. So these type of ones that are up here are more biodegradable than, say, for example, a benzene ring with 2 substitutions, so over 100 days. So these compounds on the bottom here are less biodegradable. So how do you find out? You can find out in the literature. You can do some experiments to see whether it's biodegradable or not. Depending on what kind of structure you have, these ones will also be biodegradable or not. So yeah, so really what we're interested in as engineers. So the microbial people will be concerned with what type of bacteria you have. As engineers, you're kind of more concerned about what kind of conditions you have at the site and what can we do to make the conditions favorable for the biodegradation to occur. So whether you have sufficient oxygen, whether you have sufficient moisture, the temperature is appropriate, pH, things like this, whether you have enough nutrients, and whether the carbon source is sufficient for the things. So these are the things that need to be in place basically for us as engineers and make sure that these conditions are good so that bacteria will be able to do their job. So ultimately, oxygen is the best respiratory venue to go. It's the fastest. But if there's no oxygen available, there are other alternatives for other types of bacteria. So things like nitrates, sulfates, iron, and things like this, it can also to be able to do the biodegradation, but in an anaerobic method as opposed to aerobic. So as you see, we can calculate how much oxygen we need, knowing what type of compound that you have. So on a theoretical basis, you can figure out how much oxygen you'll need to supply. The problem is oxygen has a limited solubility in water. So this is sometimes a difficulty of, like, particularly if the site is contaminated and is very deep in the subsurface, to get oxygen to that site is a bit difficult. So definitely anaerobic way sometimes is better than doing an aerobic way. So yeah, so basically you need moisture. So in groundwater, of course, it's not an issue because water is water. But if it's in the soil where you're trying to do you need to have a minimum moisture content for the bacteria to work in the soil. Ideally, oops, sorry. You need to have basically a good temperature range. I mean, bacteria can work at almost any temperatures, but ideally the 20 to 30 temperature range are probably the best ones to work at. So during the summer, as you can see, maybe even if it's too hot, sometimes they don't like too much. But basically, this range of maybe 15 to 30 is probably the most optimal. Yeah, so as I say, you can have bacteria that grow so you just have to try to get in the right range. pH is usually around the neutral pH is the best for bacteria. And nutrients, you'll need a certain amount. Sometimes in the soil you already have, so it's not really a thing. And then you could also calculate based on the amount of contaminants you have, how much nitrogen and how much phosphorus there is. So as we've mentioned, natural attenuation, you can have the bacteria can do the work on their own, no interference of humans, no engineering steps. And this is basically the natural processes that are going on. So it'll work well at maybe low concentrations. At higher concentrations, maybe it's much more difficult and will take too much time. So if the non-engineered natural attenuation doesn't work, what you could do then is add some engineering procedures, such as adding oxygen to the soil and different ways. So you can add oxygen by adding aerated water. You could add using pure oxygen. You can add ozone. You could add peroxide, because when you add peroxide to water, it breaks down, and so then you get oxygen in this way. So there are different ways that you can add oxygen to the water, to the groundwater. So procedures, as usual, site investigation, do some treatability studies, see whether you can recover as much of the contamination as possible first, and then you can implement an in situ system if all things seem to be positive, and do the monitoring and performance evaluation over time. So aquifer characterization, biological characterization, and contaminant characterization. So the bacterial characterization is kind of the added step that we haven't mentioned before. So yeah, high permeability, maybe, you know, and just make sure that you have sufficient nitrogen, phosphorus, and other things. So again, you can do treatability study if you don't know if it's biodegradable or not, that particular compound. So yeah, so you can add various things, do some monitoring. Biosystems work pretty well. They tend to be less costly than other methods. You're not really generating any waste. Sometimes the permitting is a little bit more difficult, but again, it's sort of the same procedures no matter what method you're going to use. You have to do the monitoring and make sure that things are going along as you expect. You could also do various processes as an ex situ. So if you take out the soil, you could treat things as like a slurry. So, oops, sorry, backwards. Oh. Okay. So yeah, so you could add a sort of like a soil extension, water, do the mixing, and so you can have like a slurry phase treatment this way, or you could actually do in like bioreactors where you can have even more control. But again, the more sophisticated, the more expensive. Basically how it goes. So you could do a multi-step process, something like this, remove the uncontaminated, oversized materials, do the treatment in the reactor, and then you have to separate the soil and the water. And hopefully you'll have some nice, clean, decontaminated soil at the end of the process. So obviously works well. You can have very good mixing. You can supply the oxygen very well. You could even degrade some contaminants that are a little bit more difficult to degrade. You could do techniques like landforming, which are it's called landforming because it really looks like farming materials. The equipment is basically a farming material. You're using tillers and things like this. You put the contaminated soil in. You just mix the soil, put some nutrients, make some bacteria, things like this. So it's kind of a very low cost. This one they did some covering to try to minimize the volatilization and also minimize the effect of rain on the process. But it's not necessary to put the cover on if you don't need. And basically, it's a low cost type of system. So this was done, actually, this was a site that was at a military site in Korea, actually, that I had visited. They put, as I say, this cover, this greenhouse type of cover over it. They put liners underneath. And then they added microbes, water, nutrients to the soil. And they did some tilling and they mixed it and did the monitoring. And I think, so yeah, that's what it looks like. And so basically, initially you had hydrocarbon contents of 3,700, and after time it went down to about 450. The benzene, toluene, ethylene benzene rates were over 80 ppm, and over time it was non-detectable. So basically, over 90 days, they've added some nutrients. They did some tilling 3 times a week, maintained the moisture content. And they monitored the contaminants and the carbon dioxide and things like this. And so it took about 90 days to treat this soil. So definitely an ex situ type of remediation. So you could also do like thermal type systems where you're heating the soil or washing like this. These are some other things. So this was the same type of biopile system that I had mentioned before. So yeah, I bring the students, actually I brought my students to the class where we visited this site this past summer. Yeah. So they treat, as I say, these contaminated oils and so on. And yeah, it works quite well, very low cost. So basically that's the system. You have, you put these covers, you just inject some air into the system, make sure the moisture content is good, and the bacteria will do the work for you. So yeah, so sometimes you can add various stuff to increase the porosity of the soil if it's not sufficient. So definitely things like land farming, composting, biopiles, all of these things are fairly low cost bioremediation techniques. So you can add various microorganisms to do the work for you. Another technique is using plants to do your work. So people have done research on grasses and trees to do the remediation. So basically, you could use the roots of the plants to uptake some of the contaminants into the plant itself. And so as you see that there are a whole bunch of remediation mechanisms that are going on here with the plant. So the issue is you have to find plants that are tolerant to the contaminants, obviously. And also, what do you do with the plant when it becomes contaminated? So this is the bit of the issues that you have to deal with. Yeah, so as I mentioned, there are a bunch of mechanisms, the volatilization, sequestration, extraction, and so on. So yeah, so in situ bioremediation, just going back to the microbial process, there are different ways you can add oxygen, nutrients. So this is just a way you can inject it into the water just like this, and so on. You can modify the soil vapor extraction method that I mentioned before. So really this as you see is kind of the same type of setup as we did for the soil vapor extraction. The difference is you use lower flow rates of air. So the whole idea is to stimulate the bacterial growth as opposed to the volatilization of the contaminant. So you can do air sparging, which is just like the air sparging, which I mentioned before. So again, you're trying to stimulate the biodegradation as opposed to the sparging, as opposed to the volatilization of your contaminant. So so those are just ways of doing it. So this shows you an overview of, in the US, what type of techniques are used in situ and ex situ. So you see pump and treat are quite common, phyto to some extent, bio to some extent, thermal treatments and things like this, chemical treatments, which I'm going to mention a little bit, the soil stabilization and so on. And there are also some bio type of systems like wetlands and so on are used, and phytoremediation is used somewhat, but not. So it just gives you an idea of some of the techniques that are used. So again, you develop the model, what's going on, do your treatability studies, do some pilot studies, and design your process. Try to minimize the operation and footprint of your process, and hopefully improve your remediation. So basically, you're trying to use as sustainable a remediation process as possible, whereas you're reducing the water, reducing the energy, and reducing the greenhouse gas emissions while you're doing the remediation. So that's basically what green remediation is. Try to reduce the footprint of cleanup with remediation. So you can do all sorts of metrics to do the thing, and then you could, make sure that you minimize the techniques. So yeah, these are just some of the comparisons. Again, what kind of effect do the various treatments have on the contaminants? What scale are they at? Are they beneficially used? Are they generating any waste? And what kind of requirements do they have? And in terms of the cost. Sorry. So things like soil flushing, soil vapor extraction are fairly low. Phytoremediation costs are pretty low. Things like thermal desorption are fairly high. Vitrification, where you're using a lot of electricity, basically melting the soil, is also a very high cost process. Yeah. So then that brings me to the last one. So So this one, yeah. Okay, so we'll do this one quickly. So the last sort of techniques I'll mention is stabilization and solidification. So often it's used for hazardous waste, but it can also be used for contaminated soils as well. It could be done as an in situ, as I mentioned, in the soil itself, or it could be done as extracted soils and done somewhere else. So the idea is with the, so basically you're adding cement to the soil to reduce the leaching of contaminants from that soil. So there are a whole set of mechanisms: fixation, solidification, stabilization, and so on, which you're doing by adding these decontaminating areas to your soil for stabilization purposes. So you're doing a physical entrapment and a chemical stabilization at the same time. So you're adding all sorts of things like fly ashes, and so you have absorption, you have precipitation, you have detoxification, and you have all sorts of binders and sorbents that you're adding. So the most popular solidification method is to add Portland cement. So things like heavy metals can be fixed this way. But organics don't work quite as well, so you might have to add some other types of things. So pozzolans are also used for inorganic materials. Lime is also used for inorganic. And if you're going to use organic, you might have to do some modification of these from these different types of cements to organically modify it to have better compatibility with the hydrocarbons. So, and a more extreme process is doing vitrification. Basically, what you're doing is you're putting a current into the soil and you're actually melting the soil. So, so basically, you're doing it creates a very high temperature situation, and that's how you're able to melt the soil, because basically you're subjecting the soil to about 1600 degrees Celsius. So it treats all of the organics that are inside. The inorganics will then be trapped into this melted soil, and this basically forms like a glass-like structure within the soil. And because of the no pore space in the soil anymore, you have to add a bit of backfill to make up for the subsidence. And so you could also do it ex situ by doing it in a vessel, separate vessel. So that's the in-plant vitrification, as mentioned here. So yeah, so basically you're melting it, cooling it, and because it's like a glass, so if you're doing it as an ex situ, you could actually form this glass-like material, and you could reuse it for other purposes, really. So thermal extraction is basically heating your soil, and so you can use things like fiber optics. You can use various types of radio frequencies, hot air, steam injections, all sorts of things to increase the volatilization of contaminants in the soil. So basically the idea is that you're bringing up the temperature, it increases the volatilization. So it works well with organics, works well with methyl, mercury, and things like this. You can also incinerate your soil, which is also quite a frequent use for highly contaminated soils. Things like dioxins and things like this. You obviously need very high temperatures to do that. So these leaching tests are basically a way to see whether your process has worked very well. So if you're adding these cements and things like this to your soil, you can see after the treatment whether you're decreasing the leaching of your contaminants from that soil or not. And so there are different types of leaching tests that are used to see whether this is working well. So this toxicity characteristic leaching procedure is kind of the test that's used. You crush the material, you treat it with acetic acid, you filter it and so on. And so then you compare it to these levels. And so if any of the contaminants exceed these levels after the treatment of the leaching, then you have still a hazardous material. If it's lower than these levels, then your method is now successful. So it's maybe an extreme treatment method, an extreme leaching procedure, and not very realistic, but it kind of gives you a worst case scenario. So there are different tests that are used, but a lot of them are not used very frequently. Yeah, so all of the chemical analysis done for metals, gas chromatography, things like this, total organic carbon. There are a lot of techniques that are available now, FTIR for certain bands, doing things like gas chromatography with mass spec, ICP-MS for heavy metals, atomic absorption for heavy metals. There are all sorts of techniques, and the level of, and of course you have new contaminants that have been identified, like PFASs and things like this, as new contaminants of concern. Some of these other tests I've mentioned before, looking at the cone penetration tests, looking at the hydraulic conductivity tests. You could use X-ray diffraction, as mentioned, to see what the characterization of your soil is and so on. So that's basically vitrification. And these are some of the in situ processes for solidification and so on. So you can, as you see, you can add the material into the soil at the site. So these are the in situ process for doing solidification. So you can do some grouting methods and so on. So I think actually, yeah, that's it. So basically this is the schematic, which I've been sort of mentioning through the course, you know, doing the site characterization, looking at the hydrological settings, looking at what's at the site, seeing what type of things need to, doing the characterization of the contaminants at the site. What are the properties? Are they volatile? Is it biodegradable? Is it soluble? Is it hazardous? Obviously, to begin with. Do we really need to do something for the first place? And look at then what the options are for the remediation. So you need to identify some short lists of what type of options are available for the remediation. Consider which ones could be more thing, do a very, very short list. First of all, whether it's feasible or not. Then if it seems to be feasible, try to look at the economics of using that particular type of remediation. Then you could go to very small tests, what we call pilot tests, whereas you'll just take a small section of your contaminated area and do some testing at that particular area. So you can then test out some of the design procedures at that particular site. And if that seems to work, then you can develop the full-scale remediation. And oops, sorry. So based on the full-scale remediation, you do all of the design and so on, and then hopefully implement your procedure, go about it, do the monitoring and so on, and then hopefully eventually achieve decontamination of that particular site, and then do your cleanup. And hopefully everything will be closed and you can go on to other jobs. If not, then you might have to go back and do again some of the other procedures that you maybe eliminated first of all, and then maybe you might have to go back on that. So that's kind of the overview of the geoenvironmental aspect. Try to use green procedures as much as possible. Try to minimize the greenhouse gas emissions, the energy uses, water uses, things like this as much as possible when you're actually doing the remediation. So, I mean, there are some other methods, of course, and so on, but those are some of the methods that are available, some of the key methods that are available. So if there are any other questions, I'm obviously available for that. If not, I thank you for your attention.
Okay, we'll see if the online comments worries some of the questions. This one here. That is the
that's
question
the one
from
that I
the
did. Yeah,
in the morning. Seems like we got no further questions in the afternoon's course. Now, maybe we can end the course today.
Yep. So thank you. Thank you for your attention, everybody.
Good job.